All right, welcome ladies and gentlemen. This is the first of our two videos on buffers, which is a secondary topic in equilibrium. So throughout this series of videos, these two videos, I'm going to be talking about basically what is a buffer, what do buffers do, what are the components of the buffer, why am I still insisting that you make little lists of ions that you have in solution, why do buffers work, that's actually those three things are going to be the first video. And then how to pick the best buffer for the job, how to make a buffer. There are actually two ways that you can create a buffer. And then lastly, calculations involving buffers. So what you might be able to tell from this list is that it's actually more important that you understand the qualitative aspects of buffers and that you can't just do calculations with buffers. Calculations with buffers are important, but it's really a lot more important to understand if you have a buffer, how a buffer works, what do you need in order to have a buffer, how to pick out a buffer, how to recognize a buffer, things like that. So this is a secondary topic of equilibrium, and this is probably the most important secondary topic in equilibrium. We are still absolutely using our skill set from primary topics, so you still have to be able to write an equilibrium expression, plug in, use ice charts, etc., etc. But buffers are a really important topic, and the AP loves to ask about them. So this is a big one, big important secondary topic. So what is a buffer? The definition of the verb to buffer, which you have, I think, heard before in everyday life and probably even used it, simply means to protect or lessen the impact of something, to protect against something. A bumper is kind of like a buffer on a car. It can lessen the impact of something, of the car with something. A chemical buffer, so in this context, talking about a buffer with chemistry, it is a solution that resists change in pH. So that's what a buffer is. It is capable of resisting change in pH when you add an acid or a base to it. So it's something that you add some strong acid or some strong base and you actually don't get a huge pH change. You get a very minor pH change, and that's a buffer. It moderated the impact of that added strong acid or strong base. Our blood is an example of a biological buffering system. Our blood is designed to be able to withstand additions of small amounts of strong acid and strong base without getting a huge shift in pH. And that's really important because a lot of our biological systems can only function properly within a very narrow pH range. So we need our blood to kind of make sure that nothing crazy happens, that our pH doesn't get too high or too low. What are the components of a buffer? Basically, what do you need to have a buffer system? And there are two components. Every buffer needs two things, it always has to be two things. A buffer needs a weak acid and its conjugate base. A weak acid and its conjugate base. You could also have a weak base and its conjugate acid. That works too. That makes a buffer. AKA, the thing that you need is a weak, and that's huge, conjugate acid-base pair. So you need, for example, HA and A minus, right? Or you would need, if it's a base, you'd need B and HB plus. It has to be weak, and you have to have both of them. Remember, weak acids do not react with their conjugate bases. And that's kind of the important part of like why you have buffers, right? HA does not react with A minus, B does not react with HB plus. But if you have both of those things together in the same system, a weak acid and its conjugate base, or a weak acid conjugate base pair, because it could be a weak base and its conjugate acid, then you have a buffer system. You have a system that is capable of resisting change in pH. So you have to have those two things. So for example, a solution consisting of both acetic acid, HC2H3O2, and sodium acetate, NaC2H3O2, it would act as a buffer because you have acetic acid, which is definitely a weak acid, and then you have sodium acetate, which is 100% soluble. So it's going to dissociate, and it's going to split into Na plus and C2H3O2 minus as soon as it hits the water. And you have this thing right here. Now this is the conjugate base of the weak acid. So you have both of them together. You have a weak acid and its conjugate base. Boom, you have a buffer. Notice how we focused, the sodium doesn't matter at all, right? But you still kind of need the sodium because you cannot buy a beaker of just acetate. You can't do that. It's an ion, so it always has to be paired with another ion. So you need kind of a delivery mechanism, and that's going to be the sodium. But you have the acetic acid and the sodium and the acetate ion, boom, you have a buffer. But if you have a solution that contains both hydrochloric acid and sodium chloride, well, you do have an acid conjugate base pair because you have HCl and you have NaCl, which is going to split completely into Na plus and Cl minus. So while yes, you have that and that, this is a strong acid, and this is the conjugate base of a strong acid, which is neutral, remember, right? It doesn't really do anything. And this will not work. It cannot be, buffers cannot be strong acids, and so we certainly can't use the conjugate base of a strong acid. That is not a buffering system. It has to be a weak acid. We're going to look at why that is. So it has to be a weak acid or a weak base with its conjugate. So HCl would not work as a buffer system because it's not a weak acid. How does a buffer work? This is the rest of the video. I'm going to be talking about this. How does this weak acid conjugate base system work to protect against pH? The main idea is right here. A buffer system can convert a strong acid or a strong base into a weak acid or a weak base by simply reacting with the added strong acid or strong base. Meaning you have that system set up, you add in a strong acid, strong base, the buffer actually reacts with it and converts it into not a strong acid. It actually converts it into a weak acid. And the weak acid or weak base that's generated, it does not affect the pH nearly as much as the strong acid or the strong base, because that's simply the definition of strong versus weak acid. A weak acid does not completely dissociate, so you do not get nearly as much H plus ions from it. So we take a strong acid, we turn it into a weak acid through a reaction, and we get something that will not affect the pH as much. We resist that change in pH. We are not going to be altering the amount of H plus or OH minus ions significantly. So, showing you with some beautiful particle diagrams, which I found online, and I'm totally in love with these. Addition of a strong acid or strong base without a buffer. So let's just consider water, which is not a very good buffering system at all. So let's just consider water, and we add HCl to water. So this is our HCl, and we're putting it in the H2O, and the HCl, because it's a strong acid, it donates all of its H plus ions to water, and that's our reaction right here, right? So the H plus is getting donated to the water 100%, and we generate a huge amount of hydronium ions, right? We have lots more H3O plus. That's bad. That's bad. We're going to have a very, very big change in pH because of that, right? We get a huge shift. We get a lot of hydronium ions. Well, okay, you've just really changed your H plus concentration significantly, so you're going to have a really, really big change in pH. So we don't have a buffer system there. The HCl donates all of its protons to water, and we get this really big increase in the amount of H3O plus. So that's not a buffering system at all. Let's consider adding a strong base to the buffer, to water, which again is not a buffer. So we have a strong base. So again, this is this 100% complete dissociation. All of the sodium hydroxide is going to dissociate. So we get a huge increase in the hydroxide concentration, right? Lots more of this sucker. We've got it here, 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 here. Oh, all over the place. Look at all those hydroxides, right? A huge increase in the amount of hydroxide ion. So we're going to get a really big pH change because of this. We don't have a buffer system. You add in a strong base, you get a huge shift in the amount of hydroxide, and you don't have a buffer, you're going to get that big pH change. But now let's consider a buffer. So this slide is simply showing making the buffer. So, okay, let's take a weak acid, HA, and its conjugate base. So, right, this is our HA, and this is our A minus. When we combine them, now we have a buffer. We have both. We have both a weak acid and its conjugate base at the same time. Remember, they don't react with one another. HA does not react with A minus. I've been saying that, I feel like, for like 5 videos now. The weak acid and conjugate base, they remain in solution, right? HA is still going to be mostly HA, right? You look here, this is, you know, HA, and we only get a tiny amount of dissociation off of the HA because it's a weak acid. So it's mostly HA. They stay in solution. Likewise, the A minus, it's not really going to react with water all that much because it's a weak base. This is the fundamental difference in definition between a strong acid and a weak acid, between a strong base and a weak base. So you have HA and H minus, HA and A minus, they're going to stay in solution. They won't really react with water all that much. Yes, they will a little bit, but you know, more than 95% of it will stay as HA and A minus. So you have this weak acid, weak base together in solution. Now let's add, first of all, some sodium hydroxide to this buffer and consider what happens. Couple key points about this. When I'm adding sodium hydroxide to this buffer, I'm only adding a small amount. So I'm not talking about like taking a 5-gallon tank of NaOH and adding it into this buffer. I'm talking about adding like, I don't know, 10 milliliters or so. So a small amount into maybe what was a very large amount of buffer. So you add in the strong base. HA is going to react with it, right? So we're going to have the weak acid here reacting with the strong base because, you know, that's what acids and bases do. So you add in the hydroxide will not react with the A minus in solution, it will react with the weak acid in solution. The acid reacts with the base. Now, when this happens, this is a one-way reaction, and that's actually a really critical point. This is a neutralization reaction. This right here is neutralization. I don't care if it doesn't look the way it looked in Regents. It is an acid and a base reacting with one another. And what is happening is the acid is donating its proton to the hydroxide. So we have the acid doing what an acid does and the base doing what a base does. The acid donates its proton, the base accepts it. But this reaction is not an equilibrium reaction. Meaning it goes and then it stops. It's one way. Notice the arrow, it's one way. Right, that's a one-way arrow. So it goes until something is used up. Until something is used up. And because we added a small amount of hydroxide, the thing that gets used up first is the hydroxide. So this is going to run until the hydroxide is used up, because that's part of our sort of definition of a buffer system. We have a large amount of weak acid and weak base, and we add in a small amount of, in this case, strong base. So this reaction runs until the hydroxide gets used up. But look at what we made. Look at what this neutralization reaction, all neutralization reactions, by the way, are not equilibrium reactions. They go until something is gone. We made something that doesn't affect pH. So this reaction created more A minus. A minus does not react with the water very much. We took our strong base, our hydroxide, we combined it with a weak acid, we neutralized it with the weak acid. The weak acid created A minus. It created a weak base. It created something that does not really react with water all that much, something that does not like to dissociate, something that does not like to accept a proton. It created something that doesn't affect pH. Notice how hydroxide or hydronium ion are not products in this reaction. A minus and H2O are. These are things that do not affect pH very much. And pointing this out too, we already had A minus in our solution anyway. So we're generating something that we kind of already had. We're not starting from scratch here. We already had A minus. The end goal from this is that we do not see a major pH change. We added in hydroxide, but by reacting it, neutralizing it with a weak acid, we're created something that will not affect pH all that much. No major hydroxide concentration change. Right, our pH winds up not really changing. Yeah, we used up some of HA and we generated a little bit more A minus, but these things don't react with water. They don't have big influences on pH. And that's how a buffer works in the case of adding a strong base to a buffer. You add in the strong base, it turns it into a weak base through this neutralization reaction, which doesn't affect pH. Looking at it from the other side, looking at it by adding in some strong acid. So we add some HCl to the buffer. Again, I have to stress that we're only adding a small amount here. We're not adding like crazy amounts of acid or base into a buffer. Now we have the flips process happening. So now we're adding in a strong acid. That's our HCl, and it's going to react with the weak base component of the buffer because acids and bases like to react with one another. That's what they do. So the base component now reacts, and it's going to react with the acid until the H plus is completely gone. This is the neutralization reaction. This is a one-way reaction. All neutralization reactions are one-way. They go until something is used up. In this case, it's the strong acid that's going to be used up because I'm stressing that we're only adding a small amount of it. And we see from this reaction right here, this is our neutralization reaction, that our acid does what acids do. It donates its proton to the base, which in this case is A minus. But then look at what we made. We made HA and we made Cl minus. Again, we're creating things that do not affect pH substantially. We created a weak acid. We created something that does not like to dissociate, something that does not like to donate its H plus ion at all. HA doesn't really react with water much, right? It's a weak acid. It likes to stay as HA, not H plus and A minus. And we already had it there anyway, right? HA was already in solution. So we added this HCl to this weak base, and we created something that is actually a weak acid. The buffer quite literally turns a strong acid into a weak acid. So we're not changing our H plus concentration greatly. We're keeping it approximately the same. We wind up seeing a much smaller change in pH than you might expect by adding in that strong acid into the buffer. No major pH change. And that's what a buffer does. That is the big thing about what a buffer does, and that's hugely important, and this is how it works. So that's the first video, and I did want to split this up because there's a lot to talk about with buffers. So that's the first video. In the second video, we're going to be starting to look at picking out buffers and how to make a buffer and some